Sentiment analysis of text and audio data. Abstract sentiment analysis has shown a significant amount of growth in the past few years. Textual sentiment analysis has been quite common as well as popular amongst researchers. Here we have first studied the approaches proposed by various researchers regarding sentiment analysis of all modalities of data. And then we tried implementing some of those methods. In this paper we have not only focused on sentiment analysis of text but also talked about audio data. Audio sentiment analysis is an area that is still being explored by researchers and hence new techniques are being utilized to analyze audio data. Here we try utilizing deep learning in order to classify audio into various sentiments. For text, we have tested basic machine learning models and have tried to draw a comparison between the results. Keyword sentiment analysis, natural language processing, feature extraction, machine learning, SVM, CNN, image classification. Introduction. Sentiment analysis is the method of detecting the emotional tenor behind a sequence of words in order to get an understanding of the opinions and attitudes expressed within a piece of data. It is predicted that about 80% of the data in the world is unstructured or unorganized. Huge amount of data is produced every day that includes emails, social media chats, blog posts, reports, surveys and other online documents. But it is very difficult to examine, recognize, and understand this data and the process is expensive and time-consuming. Sentiment analysis, on the other hand, helps in making sense of all this formless data by automatically processing and classifying it into various emotional categories. Nowadays, with the widespread of network, people have transformed the way in which they express opinions. Now, it is done mostly through blogs, online forums, product analysis sites, social sites etc. So, billions of users are expressing their views online. These social platforms help people to interact with each other and share their views regarding any product or service. Social media is producing a huge amount of opinion-enriched data as posts, comments, reviews, etc. Social media platforms also allow businesses and companies to remain in touch with their customers and keep getting their valuable feedback and suggestions. This enables them to make better decisions based upon consumer feedback. Nowadays, when a person plans to buy something he or she definitely prefers to read or view reviews online to get better understanding about the product. However, the volume of data generated online on a daily basis is way too large to be analyzed manually. So here comes the role of sentiment analysis. Opinion mining or sentiment analysis is quite useful in monitoring of social sites as it gets a summary of the sentiments of the society on every topic. The ability to take out valuable information from social data is an exercise that is being extensively used by organizations all around the globe. Some popular sentiment analysis applications include monitoring of social sites, management of customer support and analyzing customer response. Automatic sentiment analysis can be performed on any data source, to categorize survey responses and chats, Twitter and Facebook posts, or to scan emails and other documents. All this is significant information for the companies and can make them take decisions accordingly. With its growing demand and advancement in sentiment analysis techniques, the analysis of sentiments is not only limited to textual data. Researchers are even exploring new possibilities in analysis of other modalities of data. Today, with the increased utilization of internet surfing, the enormous info produced is not only in textual form but more and more images and videos are being used to convey one's opinions. There has been significant amount of research on analyzing textual data, but research related to other modalities of data including image, speech, and video content has been limited. One multimodal emotion detection is a recent topic in the domain of sentiment analysis. In multimodal sentiment analysis we also take care of the audio and visual context of the data. This can be employed in building virtual assistants, analysis of YouTube videos and depression monitoring. 2. Related work. In this section, we have briefly described some of the approaches used by researchers in sentiment analysis of text, image, audio data. A classification of textual data. In 2, the authors have performed sentiment classification on Twitter dataset. Firstly, they used naive Bayes as a baseline algorithm on unprocessed data. Later they performed pre-processing of dataset followed by stop words removal in order to draw a comparison between the results. Then they used various machine learning approaches like SVM and maximum entropy. They experimented with unigrams, bigrams, stop words removal, finally achieving the best results when using SVM with unigram or bigram. In the research performed in 3, a rule-based classifier called VADR was presented. VADR stands for Valence-Aware Dictionary for Sentiment Reasoning. It is a rule-based classifier based on lexicon that can detect both polarity and intensity of the emotion. It was made to compare with 7 well-known lexicons at that time, and it outperformed all of them in case of social media data. In 4, the authors have presented a way for combining the machine learning models as well as background knowledge of lexicons for effective sentiment classification in the form of pooling multinomial. They have presented a hybrid approach by using naive Bayes algorithm that combines lexicons knowledge and the training of the classification model. Datasets were extracted from IBM Lotus blog posts, political posts, and movie reviews, and it was found that linear pooling model performed well as compared to various other approaches. B. Classification of audio data. In 5, the authors have suggested ways to use the acoustic features extracted from audio signal in order to detect the emotional status of the speaker. The speech signal was fed to the voice activity detection system as input that recognizes and differentiates audio from speech signals. The audio was then fed to ASR model and speaker discrimination model for identifying the data and speaker identity. ASR model then labeled the voices with different speaker IDs. The voices were then converted to text with the help of automatic speech recognition system. Then the speaker IDs were further matched with the converted text. The text output produced from the ASR system respective to different speakers was a significant feature to predict the emotion expressed by different speakers. In 6 research, end-to-end ASR models were used to combine acoustic features with text for sentiment classification. Here, RNNT model was utilized to perform end-to-end speech recognition, then the result was fed to sentiment decoder. Sentiment decoder consisted of BiLSTM, attention model, and softmax classifier. To reduce overfitting, spectrogram augmentation was implied. The authors were able to achieve in 7, the authors extracted text and acoustic features separately from the input. They have used HM model for classifying acoustic features and naive Bayes and SVM for text features. Final output is produced after combining the results obtained from both type of classifications. This study showed the importance of both text as well as acoustic features in sentiment identification of audio data. 3. Text sentiment analysis. A process of text sentiment analysis. 1. Collection of data. The very first step is to collect the data on which we want to do sentiment classification. 2. Pre-processing of data. Before performing any operations on the data needs to be cleaned and pre-processed. This includes removal of punctuations, stop words, and other unnecessary features of the data that are not required for further processing. 3. Feature extraction. The pre-processed data is then converted to feature vectors so that they can be fed to different classifiers. The feature vectors are the kind of numerical representation of text data. Feature vectors are much easier to work with if we are using machine learning models. 4. Training the model. After the text has been converted to feature vectors, the dataset is split into training and testing data. The models are trained with the help of labeled training data using suitable classification algorithms. Table I. Comparison table. Researchers' names and year. Model used. Type of input data. Results. Card, Vishal, and Professor Sonawane 2. Naive Bayes, SVM, and maximum entropy. Text. It was found that SVM with bigram model gave the highest accuracy. Hutto, Clayton, and Eric Gilbert 3. Vader. Text. Vader outperformed the current state of the art in case of social data when compared to other lexicon-based models. Melville, Prem, Wojciech Gryc, and Richard D. Lawrence 4. Multinomial naive Bayes. Text. It was found that linear pooling model performed well as compared to various other approaches. Magilnan, S., and M. Rajesh Kumar, 2017 5. ASR models, naive Bayes, linear SVM, and Vader. Audio data. Among ASR models, Bing Speech API gave the highest WRR. Among classification models, Vader was the most effective one. LU, Zioun, ETL6. RNNT model, BiLSTM, attention model, and softmax. Audio data. RNN with attention and spec-aug proved to be way better when compared to other RNN pooling/attention models. Murika, Aishwarya, ETL7. Naive Bayes and SVM. Audio data. It was found that better results can be obtained when text and acoustic features both are combined to produce the final output. 5. Evaluating the model. Finally, the trained models are tested and evaluated using the test dataset. B dataset. Here we have used IMDb Movie Review dataset for sentiment analysis of textual data. This dataset consists of 50,000 movie reviews, out of which 2,500 are labeled as positive and 2,500 as negative. We selected this dataset because there is an equal distribution of both kinds of sentiments. See models. We have experimented with different machine learning algorithms such as SVM, naive Bayes, logistic regression, and KNN. 1. Support vector machines. It is a non-probabilistic model that makes use of a representation of inputs as points in a multidimensional space. It draws a hyperplane in the multidimensional space for classification of input. Each category or class is assigned a separate region in that space. New input is classified based on its similarity with existing data points and regions. 2. Naive Bayes. It makes use of Bayes' theorem to predict the possibility that an input belongs to particular class of labels. It assumes that the features are independent and the occurrence of one feature does not affect the other. It is a simple probabilistic classifier and yet performs well in sentiment analysis tasks. 3. Logistic regression. It works on the basis of a sigmoid function that always gives the value in between 0 and 1 irrespective of what the input is. This makes it suitable for classification problems. 4. KNN. It compares the input with its k-nearest neighbors and assigns the label based upon the majority indicated by the k-nearest neighbors. 4. Visual sentiment analysis. A process of visual sentiment analysis. 1. Preparing the dataset. Our dataset contains grayscale face images of 48*48 pixels dimension. Each of the image depicts one of the given emotion class that is angry, surprise, happy, disgust, fear, neutral, sad. The dataset file has two fields, namely emotion and pixels, where emotion field contains numbers from 0 to 6 as per the emotion depicted by the image and the pixels field contains a string with space-separated pixel value for each image in row major form. Our major job is to train the model so as to predict the emotion field. 2. Pre-processing the given data before proceeding forward. The given data is pre-processed using the techniques such as resizing, reshaping, converting the image to grayscale and normalization. Normalization is done so as we can achieve convergence as fast as possible. 3. Splitting the dataset. The given dataset is split into two parts, the training set and the testing set. This is done so that we can know if the model is overfitted to the training set with the help of the testing set, also known as the validation set. 4. Building the model using deep neural network. The DNN consists of mainly two kinds of layers. The hidden layers / feature extraction part, O convolutions. O pooling. The classifier part. Further, the following layers are added. Convolution layer. A set of learnable filters are used in this layer. A filter can detect specific features or patterns present in the input image. Pooling layer. This layer is used to reduce the know of parameters and computations. It also controls overfitting by reducing network spatial size. Batch normalization. In this, the layer inputs are standardized so that we can speed up the learning process. Activation layer. This layer uses an activation function that is responsible for deciding the final value of a neuron. Dropout layer. This layer is basically responsible for preventing overfitting of model. Flatten layer. In this layer the data is converted to a 1D array, flattening, before passing it to the next layer. Dense layer. The dense layer is a fully connected layer, which means all the neurons are connected to each other in the current and the next layer. 5. Train the model. To train the model means making it learn on a repeat. Now a few hyperparameters are defined, like the know of epochs, batch size, rate of learning, etc. Here we look for the best parameters only by trying them repeatedly by changing the values of these hyperparameters. For recording the performance of the model during the period the model is training, various types of callbacks are used. Some examples of callbacks that we use are: A. Early stopping, is used to stop training when a monitored metric has stopped improving. B. Model checkpoint, to save Kara's model or model weights at some frequency. 6. The new model is evaluated. We check for the performance of the model, i.e. how well the model is learning patterns from the training dataset. In this we test that how the accuracy is changing upon increasing the number of epochs. For this purpose we use Matplotlib to visualize the model with the help of a learning curve. 7. The model is tested. In testing, the model is used for prediction of some images. Here in testing also, the test images are also pre-processed before they are passed to the model. 8. The model is saved for further use. For saving the model, both the weights and the architecture are saved into .h5 file and .json file respectively. This is done so that we don't need to train the model every time we need to predict the emotion of the images. So now on we can load the model, make the predictions. B. Dataset. Here we are using the Kaggle_FIR 2013 dataset, which is freely available on Kaggle. It includes 35,587 images and we worked on the FIR 2013.csv file. This file contains two fields, namely emotion and pixels. Another dataset that is used is the RAF_dataset, which contains 15,399 basic images and 3,954 compound images. V results. A text sentiment analysis. The results that we obtained with 3 different classifiers, namely Logistic, Regression, SVM, and Naive Bayes in 2 categories, with and without stop words, are presented in Table 7. As evident from the table, stop words removal have made a slight increase in accuracy of almost all the models. Support Vector Machine, SVM, performed the best as compared to Logistic Regression and Naive Bayes. However, Naive Bayes shows the highest amount of increase after stop words removal. 6. Conclusion. After going through the work of different authors, we have come to know that all the experiments that were carried out yield either a positive or negative sentiment polarity or emotions such as happiness, love, anger, fear, and sadness as an output. We also came to know that we can achieve better results by combining different modalities such as visual and textual as compared to using one at a time. The results that we have drawn from the study of these works are summarized in Table 1. For text classification, lexicon-based approaches tend to execute faster as they do not require training of the dataset and are effective for small volumes of input data. However, these approaches rely completely on lexicons, and if a particular word cannot be found in the dictionary, then it cannot classify that word. On the other hand, in order to work with large volumes of data, machine learning models can be utilized and can perform better. This requires a lot of pre-processing on the data so that it can fit into the model. Many researchers have proposed hybrid approaches that use both machine learning models and the background knowledge of lexicons. These models have also shown good results as they combine the best of both the methods. As evident from the table, stop words removal have made a slight increase in accuracy of almost all the models. Support Vector Machine, SVM, performed the best as compared to Logistic Regression and Naive Bayes. However, Naive Bayes shows the highest amount of increase after stop words removal.